Hello, in this presentation we will be talking about a new kind of isomer that we haven't talked about before, specifically dealing with the fact that because carbons are tetrahedral, if you have two or more groups on different carbon atoms of the same ring, if we have two methyls or two ethyls, or in this case a methyl and an ethyl, on different carbons, so in this case it's the 1 and the 3 carbons, then they can be either on the same face of the ring or on opposite faces, or it's the same side or on opposite sides. So for example, here is a cyclopentane ring, doesn't matter the size, but this happens to be a cyclopentane ring. We have this methyl group that's up above the ring, and this one's down below the ring. So think of the 5-membered ring as being in the plane of the screen, then this one is in front of the screen, and this one is behind the screen. So they're on opposite faces. I've made a model of that. And notice that here's a methyl group that's coming out towards you, and an ethyl group, a 2-carbon group, is going away from you. So one is on this face of the ring, and the other one is on this face of the ring. That situation is called trans. So this particular compound is called trans 1-ethyl 3-methyl cyclopentane. This is another way of representing it. It's what's called a Haworth diagram, where the 5-membered ring in this case is drawn in an attempt to make it sort of parallel to the floor. And you'll notice that this methyl group then is above the plane of the ring, and this one's below the plane of the ring. So they're on opposite sides, and so we call that trans. So here's trans, 1-ethyl 3-methyl cyclopentane, 1 up and 1 down, or 1 up and 1 down. This would be the cis isomer. So I've modeled that as well. Notice that if I hold it this way, the methyl group is coming out towards you, and the ethyl group is also coming out towards you. Make it look a little bit more like it's coming out towards you if you do that. But notice that this carbon is on the front face, and this carbon is on the front face. So they're on the same face of the ring, shown clearly here, both pointing up if the ring is parallel to the floor. This one's pointing up, and this one's pointing up. That's called cis. So if they're on the same side of the ring, it's called cis. If they're on opposite sides of the ring, it's called trans. Pretty simple idea. What is the relationship between them? First of all, are they identical? And the answer is no, they're not. These are different molecules. This one can look across the ring and see that one, whereas this one, if it looks across the ring, doesn't see anything, except this one may be underwater, so to speak. So they are different. Isomers, then, if they're not identical, are they isomers? And the answer is yes, because they have the same formula. They're both, what would that be, C8H16, but they're not the same, therefore they are isomers. The question is, what kind of isomers? So let's ask ourselves, are they constitutional isomers? Here are some examples of constitutional isomers. This, you remember, is called isobutane, and this is called N-butane. Or in the IUPAC system, this is just called butane, and this is called 2-methylpropane. Groups are connected to each other differently, so these are constitutional isomers. Same thing here. In this one, the oxygen is on the end of the 2-carbon chain, and this one, the oxygen is in the middle of the 2-carbon chain. So these are constitutional isomers. So are these constitutional isomers? And the answer is no, because the same groups are attached to the same carbons. It's just the arrangement in space that's different, and therefore they're not constitutional isomers. So, are they conformational isomers? Remember what conformational isomers are. Those are ones that you can interchange one to the other by rotating around a single bond. For example, this is butane. These two methyl groups are gauche to each other. These methyl groups are anti to each other. This one can turn into this one by just rotating around this bond, moving that methyl group up, that hydrogen down there, and that hydrogen there. So these are rotational isomers, sometimes called conformational isomers, and you remember these are sometimes called conformers of each other. We haven't really learned this yet, but it turns out that if you have a group on a cyclohexane chair form, if you rotate around all 6 bonds in the ring, what was up and sort of at an angle like that will go to still being up, but now being straight up. This is what's called axial, and this is called equatorial. That's a little preview of things to come, so don't worry about those words just yet. But the fact is, you can turn this one into this one by rotating around single bonds. So these are also what are called conformational isomers. What about these two? Can we turn one into the other by rotating around bonds? For example, here is the trans one, methyl group down, methyl group up. Can we turn this into this by somehow rotating around bonds here? Well, we can jiggle it a little bit, but the fact is, what was down will stay down, and what was up will stay up, unless we turn the molecule upside down. But then, the methyl group is up and the ethyl group is down, so it's the same thing whether you flip it like a pancake or not. They're still trans, they're not cis. In order to make it cis, I would literally have to take off one of the two groups, break a bond, break off a hydrogen, move the hydrogen down, and then switch the methyl group up. Now I've gone from trans to cis. So the fact is they're not conformational isomers. You can't get to one from the other by just rotating. So what are they? If they're not constitutional isomers and they're not conformational isomers, these are what we're going to refer to as configurational isomers. I know that's complicated because we have constitutional, conformational, and configurational. They all sound kind of the same, but you got to know those terms. Configurational isomers differ only by shape, not by what's attached to what. Everything is connected to the same atoms here. It's just that one's down, whereas that one's up. But they can't be interconverted by rotating. So those are called configurational isomers. So cis trans isomers are always configurational isomers. And as is noted here, we'll learn a lot more about a lot of other kinds of configurational isomers later on. But for now, the only kind you know about are what we're going to call cis trans isomers. So here's a flow chart, and we'll add to this flow chart a little bit as we go along. But basically, this is it. This is types of isomers. Generally, isomers are molecules that are different from each other but have the same formula. So anything that's C4H10, those will all be isomers of each other if they're not the same as each other. Under isomers, we have two kinds. We have constitutional isomers in which the order of connections is different, like, for example, N-butane versus isobutane. Those are constitutional isomers. And then we have what are called stereoisomers. These are molecules in which the connections are the same. The order of connections, what's connected to what, is the same, but somehow the shape and space is different. Now, under stereoisomers, there are two kinds that we've now learned about. Conformational isomers, in which you rotate around single bonds, so that one can be converted to the other by rotating around single bonds. And then we have the new kind, which are configurational, where they still differ from each other only by shape, not by what's connected to what, but they can't be turned into each other. And the example we're learning at this point is cis trans isomers. So we might ask, how do cis trans isomers behave in real life? First of all, can you separate this from this and put them into two different bottles? And the answer is yes. They are different molecules with different properties. And so you might go into the stockroom and find a bottle of cis, 1-ethyl-3-methyl-cyclopentane, and a different bottle of trans, 1-ethyl-3-methyl-cyclopentane. If you did, would the bottle that contained trans slowly over time turn into cis or vice versa? And the answer is no. They cannot interconvert, so they are separate compounds and they don't turn into each other. Would they have the same or different properties? In fact, they would be different. So the boiling points of these would be different, the melting points would be different, the refractive indexes would be different, the specific heats would be different, the heats of formation would be different, and so on. So they're different. Here are some other examples of cis trans isomers. This would be trans because one methyl group's up, one methyl group's down. Trans, 1,2-dimethyl cyclohexane, and cis, 1,2-dimethyl cyclohexane. Different compounds, different bottles, different properties. Here's a propyl group and a methyl group on the same ring. Happens to be an 8-numbered ring in this case. Here they're both up. Here one is up and one is down, so this is cis and this is trans. So this would be cis, 1-methyl-5-propyl cyclooctane. And this would be trans, 1-methyl-5-propyl cyclooctane. What about if we have three groups on there? Well, now notice that we can have even more cis trans isomers. We can have all three up. We could have two next to each other up and one on the opposite side down. Or we could have two up and then one in the middle down. So these three are all different from each other. They're all called cis trans isomers of each other. Now what we name them is a different story, and we'll get into that in a later chapter. But the fact is, these are all cis trans isomers of each other. They would all have different properties from each other. You can't turn them into each other. So these are configurational cis trans isomers.